Hi, this is our first lesson on organizing data, which covers Chapter 2 from our textbook and the first two sections, 2.1 and 2.2. So when we're organizing data, well, we need to make sure that that data can be useful, no matter what we're collecting that data for. Data that's not organized at all is referred to as raw data. Now, there are several ways that we can actually organize our data to become useful. The first is a table. Tables are nice because they're completely accurate. They give us all of the information and it's right there. Unfortunately, giant tables of data and numbers typically aren't that useful to us because they are very hard to understand. So the next way we organize data is through graphs because graphs are easy to understand. Graphs, well, they're visual. We can just look, and just by looking, we can hopefully draw conclusions about that data. Now, the con to that is that you are going to lose some information. You're not going to see necessarily every exact value. You're just going to see visualizations of the data as a whole. The third way is to do a numerical summary, like a mean, median, or mode, but we'll talk about that when we get to Chapter 3. So let's talk about an example. Let's say that Julie is interested in what color cars Tunxia students drive. Now, the first question we should ask ourselves with every single type of study or experiment is, well, what kind of data are we going to be collecting? Now, in this case, Julie's interested in the color of the cars. Color is a quality or an attribute, so this is absolutely going to be qualitative data. This is a very, very important first step with every type of experiment or study that we look at. The very first thing we should always do is try to take a second and recognize what kind of data are we collecting. Now again, this might seem kind of simple in this example because we're talking about what color cars, but we're going to be counting how many cars of each color. So even though this is qualitative data because we're recording the color of the cars, there are going to be numbers associated with this, and it's going to be very, very easy to accidentally think it might be quantitative. A particular place where this is a big issue is when we have a study that asks a yes or no question. Well, our data will be yeses or nos, but we're counting how many yeses or nos we get. And although that might feel like, well, since we're counting, it might be quantitative, no. A yes or no question is qualitative, the same way that the color of a car is qualitative. Now, when we organize our data, right, trying to use tables, the most common way is to use frequency distributions and relative frequency distributions, where basically we're going to try to list each of our category and kind of do columns to organize that data. So a few definitions to get started with. First of all, frequency. When we say frequency, that just means the number of times something occurs. The relative frequency is the proportion, or sometimes we give that proportion as a percent, of the observations within a particular category. So anytime you see proportion, and we're going to be dealing with proportions a lot in this class, especially when we talk about how likely things are and we talk about probability, but proportion always means the part to the whole. So the formula we use for a proportion is going to be, well, the frequency, how often something shows up, divided by the sum of all the frequencies. And I think as we go through an example, that should feel pretty natural to start doing this to describe our data. So going back to our example, so Julie goes out to the parking lot and she just starts recording her data. She just makes tallies for each car she sees and puts that into, well, this table that we see below. So she looks at red cars and she made 13 tallies. Well, that means the frequency for the red cars was 13. The white cars, well, there were 7 tallies, so the frequency was 7. Silver cars, 9. Blue cars, 4. Black cars, 10. And here's the important part. We always want to look at the total as well. And so if I sum up how many total cars she looked at 43 total cars. The relative frequency then is going to be to take each one of the individual colors. So for example, red, 13 cars were red out of the 43 she looked at. So the proportion is 13 over 43. Now, the proportion as a fraction is almost always the most accurate way we can represent the data, but it not necessarily the most useful. So typically we actually are going to turn those proportions into decimals. And 13 divided by 43 is approximately 0.3023 if we're rounding to 4 decimal places. So that's the proportion. Again, when we give it as a percent, all we do is we move that decimal place over 2 spots. And again, percents kind of feel natural to us. So a lot of times percents are very useful in trying to summarize our data. And I went through, and again, you can check my math, but I did the same relative frequency for the white cars, 7 out of 43, which ends up being roughly 16.28%, and so on. Notice at the bottom, the relative frequencies must always sum to 1, which would be 100%. Now again, depending on how you routed with the decimals, you might be a little bit off here or there, but it better be really close to 1, and if you add up the fractions, which are exact, it better add up to exactly 1. Now let's talk about how we can visualize this data with graphs. So the first graph we're going to look at is a bar graph. And so a bar graph, again, you're probably kind of familiar with this because it's the most common type of graph, but it's just making a bar, right, for each category of data. We can do these graphs either horizontally or vertically, and I'll show examples of each. And then the height of each bar is the frequency or the relative frequency of each of those categories. We do want our rectangles to be equal width because we want everything to kind of look nice and accurate, and we don't want to skew our data at all. So again, taking that data from earlier, the frequency bar graph would look like this. We knew that the red cars, there were 13 of them, so I drew my bar 13 units high. The really important part whenever you're doing a graph is to make sure you label everything. I have my colors along that horizontal axis on the bottom, and I wanted to make sure I labeled that. And my vertical axis is the frequency. And again, I want to make sure I label that too. So clearly 13 red cars. We look at white. We can see, well, the white's between 6 and 8, so that must be 7, and so on. And there's our frequency bar graph. A relative frequency bar graph is, well, the same idea, except now, see that relative frequency along my vertical axis. Now we're looking at that, well, that decimal value instead of the actual value. And if you notice, this is the exact same shaped graph. There's really no change in the size. Whether we do a frequency graph or a relative frequency graph, that's going to look exactly the same, which is very, very nice. And again, we can take a look, and I see red. Well, that looks like that's about a 0.3, so it must be about 0.3 of the observations were the red cars. Now, the exact value was 0.3023. And again, like I said, you lose a little bit of information with doing visual things like bar graphs, but it's still very, very useful. A Pareto chart is just a bar graph, but we organize each of the frequencies in descending order. So red showed up the most, so it's first, black was second, silver third, white fourth, and blue was the least frequent with only 4 cars being that color. And again, the Pareto chart just organizes it that way. Sometimes it's also very useful to do a pie chart. And again, a pie chart needs to be labeled clearly. And a lot of times we do the pie chart in terms of percentages, again, because we want to make sure our data is as usable as possible. And percentages just are intuitively easier to deal with than doing decimals or anything else. But the pie chart, again, if we add up all the percentages of a pie chart, it needs to add up to that 100%. It has to include everything. And that is the key with the pie chart. It only works if everything adds up to 100%, meaning that it only works if you're measuring relative frequencies. And again, you want to make sure that you have your, your key at the bottom, right? Which section of the pie is going to be red and white and so on. The next thing we're going to look at are going to be side-by-side bar graphs. And these are useful when you're comparing 2 or 3 separate times or 2 or 3 separate responses, and you want to kind of compare how these things look against each other. Now, we always want to use relative frequency for side-by-side bar graphs because the frequencies can be misleading if we have different sample sizes. And again, with side-by-side bar graphs, we typically don't want to do more than 2 or 3 responses or 2 or 3 separate times, because otherwise it just starts to get crowded and does not look very good. So let's take a look at an example. So let's say we want to compare the data on the marital status of U.S. residents 18 years or older, and we want to look at the data from 1990 and then again in 2006, and see if anything changed during that time period. So again, we go through the data, right? We comb through the census data, and we get our numbers in terms of millions of people. And again, we look at the numbers, and we can see, well, 1990, 40.4 million people were never married, and in 2006, 55.3 million people were never married. Well, that's definitely a big jump. More people are not married in 2006 compared to 1990. However, we don't really understand how big of a jump that is because there's clearly more people in America in 2006 as opposed to 1990. And that's the totals there, down there at the bottom. There were 181.9 million people 18 years or older in 1990. And by 2006, the population had grown by almost 40 million people to 219.7. So we need to look at the relative frequencies. And again, we're going to look through the relative frequencies the same way we did them before. We take the number divided by the total, and we just make sure that when we're doing this, we're careful that from 1990, that denominator of our fraction is always going to be the 181.9. And again, I went through, I did the math. You can check it if you'd like. Feel free to pause the video. But again, it's just division, going out to 4 decimal places, and then always, always, always checking at the end to make sure those relative frequencies add up to 1. Now to visualize, I'm doing a side-by-side bar graph. Now this one I'm doing a horizontal bar graph because, again, it's perfectly valid to do it either up and down or left and right. Again, though, no matter which one we do, we need to make sure that we have labels. So now my vertical axis is the marital status. We have divorced, widowed, married, and never married. And then the horizontal becomes our relative frequency. And again, just by visualizing now, we can see that, well, it looks like the proportion of people who were divorced, well, 2006 is in orange, 1990 is in blue, because again, we need a key, right? We need our data to be, well, very understandable. We need that key. And we can see that, well, more people were divorced in 2006 than 1990. However, fewer people were widowed, fewer were married, and more were never married. And again, we see these trends that from 1990 to 2006, more people were divorced and more people had never married relative to the population at the time. And what we would do next is probably try to grab data from, well, a more recent time. Again, go ahead another 16 years. So in, well, 2022, we would take another look at the data and see if those trends still continued or if things have changed. And of course, that lets us start kind of our study and, well, what it is we would try to do next. But for now, again, we're just talking about visualizing data, so let's move on to a third example. Now, this table lists the number of games that the last 45 starting pitchers inducted into the Hall of Fame for baseball, how many games they played. So you can see that some of them, one of them played 728 games, another played 730, and so on. Now again, what type of data are we collecting? Always that important question. Well, in this case, it should be fairly obvious that this is quantitative data, right? We're clearly collecting numbers. We're collecting how many games they played in, and that is a number. It is going to be quantitative data. Now, we want to visualize this, but again, with all those data points and all those individual numbers, it's not going to make sense to necessarily do a bar for every single possible number. So instead, we're going to group intervals of values into classes. So classes are just another name for the category into which our data is grouped. All right. And so we're going to choose individual classes. Instead of doing, again, well, separate bars for every single number possible, we're going to try to group them together into these classes. Now, there's not one correct way to choose our intervals, and sometimes you need to kind of almost guess and check. Choose a way to visualize the data, and if it doesn't look good, choose something else until it does look good, until it actually illustrates the data in a meaningful way that is not misleading. And so when we're constructing our intervals or our classes, again, it's important that we first identify the smallest value and also the largest value. And when we do our intervals or we choose our classes, and sometimes those classes are also called bins. You might see the term bins. Again, Microsoft Excel calls them bins instead of classes, but it's the same idea. When we choose our classes, we need to make sure that every data point is included. So we need to make sure we include the smallest point and we include the biggest point. And then we want to make sure that our classes all have equal width. That means it covers the same value of numbers. And the class width is the difference, meaning we subtract, between consecutive lower class limits. All right, and that can be kind of confusing at first when we do class widths. This is a very common mistake that we see fairly frequently, and I'll point it out when we actually start doing some data analysis here with this example. But I also want to point out that, okay, although I said every class width should be equal, sometimes we do have open-ended class widths. And that's usually going to be at one end or the other where we have an unbounded limit. And the easiest example I can think of is if we're trying to group people by age, you might just have the last group being 80 and older instead of trying to do 80 to 85, 85 to 90, 90 to 95, 95 to 100 type of thing. It might just be more convenient to just group them all as that category 80 or older. So again, taking a look at our set of data, the first thing we want to identify is the smallest value. I'll do it for you in this case. It's 672. And I'm going to show you an example when you're doing your homework of how to use technology, particularly Microsoft Excel, how to find these values very easily. Again, we want to use technology as much as we possibly can, but I'm going to do that in a separate video about your homework. We also want to look for the largest value, which is 738. And now we want to choose what our class width is going to be. Now again, there's no right or wrong answer for this. And we just basically want to make sure that our data looks nice and kind of makes sense, that we have small enough widths that we can see several different classes, but not so small that we have so many bars that the data is kind of lost. Now again, this is the part of statistics that's a little bit of an art form. And you might have to guess and check, but honestly, let's go by the most intuitive answer, which I think in this case, for these size numbers, would be 10. Let's go up by tens. Let's group everything by tens. Now, that means our first class, again, I need to include that lowest value, 672. And again, I could start with any number I wanted to, but visually, right, it's going to just look better if I choose numbers that end in 0. That's just how it is. So my first class is going to be from 670 to 679. Now, this is where it might be a little confusing with class widths. You're saying, wait a minute, that class width is only 9. If I take that difference, if I subtract that, that's only 9. Well, yeah, but that's not the class width. Again, class widths are when we subtract two different classes. So my second class would be 680 to 689, and the difference between those two would be 10. And it's this interesting problem in mathematics called the fence post problem, where, again, if you actually were to sit there and count on your fingers, there's going to actually be 10 numbers in that class. There's 670, that's the first one. 671 is the second number. 672 is the third number, and so on. And the 10th number is actually 679, because we need to count each end, right? We need to count the fence posts at the end of my fences. Again, I grouped all the data using technology, so don't necessarily worry about this. But in that set of data, there were two numbers between 670 and 679. And again, we could figure out that relative frequency was 0.04444, or 4.4%, and so on. And again, we take that data, and now from that data, I want to create a histogram. Now, a histogram is just like a bar graph, but we want the rectangles to touch. So again, bar graphs should be spaced out more. Histograms should touch. And histograms we use anytime we're doing data that's grouped into classes. And you can kind of see that visually down at the bottom. In between the rectangles are where each class width begins. So my first class width starts at 670 and it ends at 680. Well, it doesn't, right? The next one just starts at 680. And again, it's showing me the start of each class width. So the first one starts at 670, then 680, then 690, then 700, 710, 720, 730. And because my data ends, the data set actually ends here at 739, right? That's going to be the end of my last class width. And again, visually, it is pretty much the same as a bar graph. And visually, we can clearly see that most of the pitchers played between 720 and 730 games. And again, that's much more useful than necessarily looking through that giant mess of data. However, well, we lost some of that data though, right? In that previous example, that class width of 690 to 699 had a frequency of 7, but I don't know what those exact values were. I lost that data when I made my histogram. Now, there are other ways to visualize data that actually preserve those exact data values. The most common is what's called a stem and leaf plot. Now, a stem and leaf plot uses the digits to the left of that rightmost digit to form the stem, and only the rightmost digit to form the leaf. So for example, in the table, I had the value 695. Well, 69 would be the stem, 5 would be the leaf. And let's take a look. So again, I take that big set of data, right? We knew that in the 670s, there were two numbers. It was 672 and 678. So that last digit, the 2 and the 8, that's what I put over there on the leaves of my stems. All right, that's how I organize my data. Now, again, I am doing all this for you. What you should probably do if you're doing this, at home by hand is literally take that table of data, and as you start filling in the numbers, cross them out one at a time. And also, to make sure everything lines up properly, the font Courier New, every single character takes up the exact same width. So if you are doing this using technology, it is a great one to use for making sure things line up properly. And again, even with the stem and leaf plots, you need to include a key. So 67/2, right, the first value, really means it's 672 because you need to be clear about that. You can also use stem and leaf plots to represent decimals. It doesn't necessarily have to be whole numbers. And again, here my key says that 1/2 means 1.2, so which means that, again, that top one is all decimal values. And if you have data that's all clumped together, so that set of data at the bottom there, everything is between 11 and 27, but there's lots of data points. So we'll actually split it up to go between 10 and 14, and then 15 and 19, and then 20 to 24, and 25 to 29. And yeah, we can split it up that way too if we need to. The last thing I want to talk about in this video is distribution shape. And this is going to be a key concept that keeps coming up over and over and over again as we continue on through our course, because classifying the shape of data is going to be very important to figuring out what sort of statistics I should be using to describe this data. Now, there's typically 4 classifications for a shape of data, and in most cases, it's not going to fit exactly. To identify the shape, you're going to have to be flexible a little bit, and even experts will disagree from time to time about what shape the data actually fits. And so, again, there's a little bit of flexibility. And when we get to numerical summaries, there are different ways that we can hopefully identify what the shape is besides just visually. But like I said, that's part of that art that there is to doing statistics. I do also want to point out that the shapes really only apply to our quantitative data, numerical data, as the data has to be ordinal, or there has to be an order to it so that we can have a shape. Again, with the example of the cars, well, the shape wouldn't make sense because, well, what order does it go in? What comes first? Does red come first, or does silver come first? Well, that doesn't really make a ton of sense when you're talking about colors. So when we talk about shapes, it's always going to be that quantitative data. It's always going to be data that involves numbers. So again, our 4 distribution shapes would be uniform, where everything shows up about the same amount. Bell-shaped, which again is your typical bell curve, where the middle point is the highest and it kind of tails off both to the left and to the right about equally. Skewed right means that there's a peak, but the tail to the right of that peak is much longer than the tail to the left. And skewed left is just the opposite. The tail to the left is much longer than the tail to the right. So again, we always call the middle part the peak, and then each side is the tail. And when you're doing skewed, and I made this mistake for very, very much longer than I probably should have, skewed is always about the tail. When you talk about skewed, it's the tail. Skewed right means a long right tail. Skewed left means a long left tail. And so visually, this is kind of what these different distribution shapes would look like. Again, uniform, everything shows up the same. It's just equal values across the board. Bell-shaped would be where it's really symmetric. Again, you can kind of see that bell-shaped. And that's going to be what we really want with most of our data here in Statistics 1. And we're going to focus mostly on data that hopefully fits that bell shape as much as possible. Then the bottom two would be our two skews. And skewed right, hopefully you can see that you have that peak there right about at 20. And then to the right side, clearly that tail goes on a little bit longer, right? If the peak there is at 20 or 25, there's less to the left and way more to the right. That bigger tail to the right means skewed right. Similarly, but opposite, skewed left, well, we see that peak up there around 115, 120, and the tail goes further to the left, which means it is skewed left. All right, so that covers our first two sections of Chapter 2 of organizing and visualizing data. Like I said, I'll post a separate video to help you go through using technology to actually get your homework done as efficiently as possible. And then you'll also see a second video covering the second two sections of Chapter 2. If you have any questions, please don't forget to email me, and good luck.